So in the last week, we have seen that for the three-noded triangle, uh, which is this element, uh, this is how the local stiffness matrix of the elemental stiffness matrix is given. B is the strain displacement matrix. C is the matrix that relates the stress to the strain, and you have B again here. So this is a standard expression where the quantity dV, an element of area within the element, so this is your dV. dV has to be correctly interpreted in case of plane stress, plane strain axisymmetry. In fact, this will hold for 3 dimensions as well. And this is the standard expression that we will use at least for linear elastic finite elements. Now, now, the key point here is to evaluate this local stiffness matrix. You have to evaluate this integral, which is taken over VE, where VE is the area of this element for the two-dimensional case, and it would be the volume of the element or length of the element in the three-dimensional and one-dimensional cases. And accordingly, you will have to interpret dV. Now, performing this integration over a domain is the key step, is a key step in this process, and it was possible for the simple three-noded element to perform this integration in closed form. It may be very difficult to do in case of more sophisticated elements, more elaborate elements. Moreover, this takes away some of the versatility and the generality of the method, because the integration will have to be done differently. You would have a different set of integrands to deal with in case of different elements. So that is why we are going to study this week about schemes that allow us to always integrate over a fixed domain, or almost a fixed domain, and standardize the integration process, standardize this integration process in such a way that finite elements take a leap towards being a very generalizable numerical method. So that's what we will do mainly this week. But before that, let me take you through some of the basic important properties that a finite element that you design should have. So now we have seen that in case of the three-noded triangular element, we assume the displacements u and v for the 2D problem in the form a1 plus a2x plus a3y, and this as b1 plus b2x plus b3y. Now the point is that when we choose these functions in whatever way we do, whether we assume it or do it through other means that we are going to explore later, the elements must satisfy the property of completeness. So for a linear elastic problem, or for a problem in solid mechanics, what that means is that these displacements, these assumed displacements, these guessed displacements or trial displacements within the element must be able to resolve at least the rigid body modes as well as the state of constant strain. If it if it is not able to resolve the rigid body modes, then in a situation like this, as is shown in the cantilever, in case of the cantilever suffers deformation, elastic deformation up to this point. Beyond that, the elements that are used to discretize this part, they suffer only rigid body rotations. So there are many situations like this in elasticity problems where elements would suffer simply rigid body motions and not undergo any deformation. So rigid body modes, so in 2D translations, two translations and a rotation about the z-axis or in 3D there are six, three translations and three rotations, those must must be captured uh, by the trial displacement functions that you choose. That's the first condition. And the second condition is that constant strain states, at least constant strain states, must be satisfied. If they are not satisfied, then you won't be um, able to capture even the simplest deformation even the simplest deformation, because any deformation would cause strain. That's the fundamental definition of deformation, that deformations must lead to strain and therefore stresses. So if you cannot even capture the constant strain state, you have no chance of being able to model any kind of deformation. So as you see, these set of trial functions that we took for the three-noded triangle are kind of the minimal, because they have the rigid body modes, uh, A1 and B1. If X and Y are 0, even these are 0, A2 and A3 are 0, B2 and B3 are 0, then U and V would mean constant displacements in the X and Y directions, which is like the rigid body translation. And then B2X and B3Y together, A2X and B3Y together give you the rigid body modes. Also, the constant strain states are satisfied, because del u del x is equal to A2. So that's a constant strain. Del v del y is equal to B3. And del u del x plus del u del y plus del v del x is equal to A3 plus B2. So these uh, three strains, this is epsilon xx, this is yy, and this is 2 epsilon xy. These three strains are constants within the element, so the constant strain state is um, actually satisfied, and it's called a constant strain triangle. So that's the minimal that needs to be satisfied, and that is satisfied by the three-noded triangle. So completeness is the first property that you must have. So you must have the linear terms x, y, 1, x, y are the is the minimal trial function set that you can use in a finite element. So anything less than this is not going to work. So this is the minimal that you have to use in order to satisfy completeness. Now, what about other elements? There is a quadrilateral element, a four-noded quadrilateral element, which we will call the Q4 element. By the way, the three-noded triangle, we will call it sometimes called the T3 element, and this is the Q4 element. Nodes are here, and the displacements, assumed displacements, are these. So here we are using 1, x, y, xy as the trial functions. So when you look at this, your approximation to u and v must be such that a1 is not equal to 0, a5 is not equal to 0. Then the rigid body, if they are 0, then rigid body translations are not represented. So these two conditions must be fulfilled. Also, to have rigid body displacements, A6 and A3 must be negative of each other. So A6 must be equal to minus A3, because U, for a rigid body rotation, U would be um, minus A3y, and V would be A6x. So this would be the rigid body, this would be the U and V due to a rigid body, small rigid body rotation, and therefore this term and this term should be negative of each other. So these three conditions must be satisfied in order that you have the rigid body modes in place. So these cannot be violated. It obviously satisfies the constant strain state because x, y are included, and this would make the strain more than the constant. So that condition, this constant strain condition, is satisfied. And if these are satisfied, then the element would satisfy the property of completeness. Okay, so you need to check for every element whether it is complete or not. uh, Elements also have to satisfy the property of compatibility, which means that if you have two quadrilateral elements, so this is element number one and this is element number two, then if you have two elements, and after deformation, the inter-element boundary, which is this, should remain intact. Therefore, uh, you must have a situation where the displacements that are calculated on the inter-element boundary from element 1 is same as the displacements that are calculated from element 2. So this inter-element boundary from element 1 and element 2 must remain intact, and therefore the field variable on the common edges, the field variables must be continuous as you go across the inter-element boundary. The field variable in this case is u and v. U and v should be constant, should be continuous along this inter-element boundary. This is often violated for some elements, and we have already seen the plate element, which was the Adeni-Clau plate element, where the inter-element continuity is violated. But this is a desirable property, and most modern elements actually satisfy this. Most elements that are used in solid mechanics generally satisfy this. There are elements that are used in structural engineering that often violate compatibility conditions, but are still usable and are still used widely. But you have to be aware of this. Now, in order that the field variable is continuous on this inter-element boundary, you must have the situation that the values of the field variable on this boundary depends on the nodal values at this node and at this node only. It doesn't depend on this node, or this node and this node. So if you can ensure that the value on this boundary depends only on the nodes that make up the inter-element boundary, then you have sort of imposed compatibility in the element. So when you design an element, a new element, keep this in mind. Now, there are a few other points that I would like you to understand about a finite element solution. Now, remember, we had started from the principle of minimum potential energy, which said that over the volume, sigma ij, it's half of this dV minus work done by the body forces minus work done by the surface tractions has to be minimized for the actual solution. Will be a minimum, pi will be a minimum for the actual solution, which is why we said del pi equal to 0. So we have already gone through this. Now, if you look at our final, we put in approximations to u here, that we got approximations to epsilon, we got approximations to sigma, and we put all that together, and finally we had this equilibrium equation, which is the global stiffness matrix. The global stiffness matrix times the global displacement vector or field variable vector is equal to some kind of generalized force F. Now, if you accept this, then you will see that this quantity, which is the strain energy of the body, is equal to half U transpose K U. You can prove this pretty easily. You will see that this is equal to half U transpose KU. And this together is U transpose F. So U transpose KU is of course equal to half U transpose F, because KU is equal to F according to equilibrium. Therefore, pi is minus half U transpose Now we had applied it over the element, so I'll put the V's here. Okay, so this is the potential energy stored in the element, out of which the strain energy is half U transpose F. So the potential energy is minus half U transpose F. The strain energy is plus half U transpose F. So you are trying to minimize the strain energy. You are trying to find an approximate set of solutions U that will minimize the strain energy. Now, first thing to note here is the strain energy, which is given by half U transpose KU, is greater than 0 if U is not equal to 0. So only in the case that U is equal to 0, that this strain energy is equal to 0, otherwise it's greater than 0. And this is exactly the definition of so U transpose KU is always strictly greater than 0 unless if U is not equal to 0. And this is exactly the definition of a positive definite matrix. So this shows that K is always positive definite. K is always positive definite for a linear elastic case at least, because physically this is twice the strain energy stored, and that has to be always greater than 0 if U is not equal to 0. That's a property of your strain energy. Now, that is the first point, that K is always, the global K is always positive definite. Positive definite, you might have learned in your linear algebra courses, means that K satisfies this relation for any U which is not equal to 0. It also means that K has all 0 eigenvalues. Now this will happen, U transpose KU will be greater than 0 if U is not equal to 0. When U is equal to 0, it implies that U transpose KU is equal to 0. K is not positive definite. It means that your structure is not properly supported. If it's not properly supported, then you might have a set of linearly independent vectors, let's say U1, U2, etc., which will mean that U1 transpose K U1 is equal to 0, U2 transpose K U2 is equal to 0, and so on. So these are called rigid body modes. And if this is the situation, and your K has 0 eigenvalues, it is not positive definite, in that case you would know that your structure is not properly supported and you have rigid body modes existing in your structure. So that's point number 1. So when rigid body modes are all restrained, your structure is properly supported and is undergoing only deformation. In that case, your K is positive definite, definitely positive definite. Okay. The second point is, suppose your assumed displacements or assumed field variable contains one x and y. These are your trial functions. So it has 3 trial functions. So we say P is equal to 3 in this case. As for the Q4 element, we have this P is equal to 4 because there are 4 trial functions. Now, obviously, and these are linearly independent trial functions. So each of these are linearly independent, and we have defined linear independence in terms of when we did a little bit of linear algebra a few classes ago. So when you have a linear independent set of trial functions, your P is some value, and it obviously means that as P tends to infinity, that means when you have infinite number of linearly independent functions making up your assumed displacement, you would lead towards the actual solution, because your assumed solution will contain all the ingredients of the actual solution. So as p tends to infinity, you will obviously achieve convergence. So uh, so that means that when you have a set of trial functions and you add one more to it, and you keep on adding more and more linearly independent trial functions to it, you will obviously be moving towards an improved solution, which is closer and closer and closer to the real one. And this is known as p convergence. This is known as p convergence, which is achieved by adding more and more trial functions into the set of trial functions that you already have, right? So this is called p convergence. Similarly, if you have an element, you have elements like this in your mesh, and some dimension, let's say this height is h, some dimension of this element is governed by this number h, then as h tends to 0, you have infinitesimally small elements. That means your elements almost shrink to a point, and you have so many number of elements that you are actually solving the problem point by point. Then you obviously also achieve convergence, and this is known as H convergence or H refinement, which is carried out by reducing the size of the smallest elements in your mesh. So both of these, P convergence as well as H convergence, or P refinement as well as H refinement, are equivalent strategies to take your FEM solution closer and closer to the um, true solution. Okay. Now, how does FEM err? What are the errors in FEM? So the most normal, easiest to see is the fact that, as I said, that U turns out to be half F U transpose F, and pi turns out to be minus half U transpose F. You are trying to minimize pi, which means you are trying to uh, increase, you will in the process increase the strain energy stored. Strain energy is something like your half kx square for a spring. So when you increase the strain energy, you can do that by your strain energy increases means that you are actually predicting a lower displacement than uh, the real case, than the true case, and your system, your structure is stiffer. That means K is stiffer. The stiffness of the structure is more than the actual structure. So, in the process of minimizing pi, FEM actually increases U, which means that it consistently underestimates the displacements and overestimates the stiffness. So FE solutions underestimate the displacements and overestimate the stiffness. Okay. The next point is that what kind of polynomials do we use as trial functions? We have already seen we use 1x, y for the three-noded triangle. We use 1x, y, xy for the four-noded quadrilateral. Now, there is a difference between these two choices. Now, if you look at it, 1xy is so we can write something called a Pascal's triangle, which is written like this. So 0th order, so this is a 0th order polynomial in two variables. This is a first order polynomial, this is a second order, this is a third order, and it can go on. So if a polynomial contains all these terms, if the polynomial contains all these terms, it's called a complete first order polynomial. Okay, and you can see that this choice that we made for T3 is a first order, complete first order polynomial. In case of Q4, where we chose 1, x, y, and xy, we have chosen a first order polynomial and part of a second order polynomial, but not a complete second order polynomial. So when you choose one xy, you have left out x square and y square, and therefore your polynomial is not a complete second order polynomial. So for the sake of convergence, for the sake of understanding convergence, we need to understand the meaning of a quantity which we will call C, which is the highest complete polynomial hidden in your trial function. So both in this case and in this case, the value of C is equal to 1, because the highest complete polynomial hidden here is a first order polynomial. None of these have a complete second order polynomial in them. Now, when you choose when you choose these trial functions, you also try to, you of course try to make C as big as possible. That means you try to take as large a complete polynomial as you can. Uh, but you also additionally try to have isotropic approximations to both the displacements. So if this is a1 plus a2x plus b2y, this would be b1 plus b2x plus b2y as well. So the same basis functions are used in both the cases, so that interchanging x and y would not change your approximation in any way. So the element, when you are dealing with the element does not care about the orientation of your global xy axis. Otherwise, you will have anisotropic elements. If you add, say, x square to the u term and don't add it to the v term, you will have anisotropic elements which will depend on the direction of your coordinate axis. So in general, such a situation is avoided, and you use the same basis functions for both u and v, and make sure that changing x and y does not change the basis function. So you choose terms from within this Pascal's triangle, so that you take a balanced set of approximations for u and v. For example, you just don't add x square. If you add x square, you have to add y square as well. You can add xy, because that's interchanging x and y would make no difference. You cannot add x square y without adding xy square, right? And so on and so forth. So you have to choose terms which make interchanging x and y. Um, so you have to add terms such that if you interchange x and y, the meaning of the polynomials, the trial functions that are used in the polynomial are not changed. So these are the two things that you must keep in mind, that we try to take as large a C as possible, and we also try to look at the Pascal's triangle and choose terms that make u and v isotropic, that is independent of the orientation of the x and y axis. If you have x, y, and z, if you have a 3D problem, you have a Pascal's tetrahedron which adds a z, which is just not possible to draw on the screen, but the principle is always the same. So you try to balance the terms so that interchanging x, y, and z do not make a difference to the meaning of the trial functions that you have taken. Why is this completeness criteria important? It is important because it governs convergence of the FEM solution. So this is a result that we state without proof, but this is a basic result and a very interesting and important result. So if you have a number h which gives you some measure of mesh size, element size, then we have seen that h tends to 0 is obviously going to lead to convergence, because then your elements reduce to a point. But in general, if you have a complete polynomial of order c hidden in your trial functions, then the error in estimating the field variable, so the error in estimating, let's say, the displacements u and v, would be of the order of h to the power c plus 1. So this you can arrive at this result from a Taylor series expansion, but we are stating, we don't go into that. We just accept this result that the error in the field variables would be of the order of h to the power c plus 1, which means as you reduce h, you will reduce the error in u and v, or the field variables, as the case may be. Now, suppose your variational statement, suppose your expression for pi contains mth derivatives of the field variable. Let's say your field variable, let's say phi is our field variable. It's a scalar for the sake of simplicity. So phi is our field variable, and my variational statement contains mth derivatives of phi with respect to, say, let's say we are dealing with a one-dimensional case just for simplicity, and you have mth derivatives in the variational statement. So this is called a cm-1 problem. Don't worry about that, but you will have to take m derivatives of the field variable in order to get these stress-like quantities, that appear in your variational principle. And the error in these derivatives would be of the order of h to the power c plus 1 minus m. So if you have to take m derivatives of phi in order to get these quantities, which are mth derivatives of phi, then the error, if the error in phi is this, the error in this quantity, the mth derivative, would be this. This is easy to see. Now, therefore, both c, that is the order of the highest complete polynomial hidden in your trial functions, as well as the size of the element, govern the convergence rate of finite element solutions. So this is why we should worry about the uh, order of the highest complete polynomial, and we should try to make it balanced. If you have a two-dimensional or three-dimensional problem with multiple field variable components, then you must try to make it balanced so that it's isotropic with respect to changes in XYZ orientation. We have also seen that finite elements overestimate stiffness and underestimate displacements, and uh, and K is always positive definite unless the structure is not properly supported, in which case K will have rigid body modes, which will lead to zero eigenvalues. And we have also seen that there can be two kinds of refinement. One is I increase the number of trial functions. I keep adding trial functions to a previously existing set of trial functions, or I reduce the size of elements. They are called P refinement and H refinement, and both are equivalent because both of them will take us to a better solution. So we have monotonic, we call this the property of monotonic convergence. So strain energy is always overestimated by an approximate solution, but by doing this refinements, you can take the strain energy closer and closer towards, you can reduce the strain energy, take it closer and closer towards the correct strain energy. So with that, I finish the properties that finite elements must satisfy. You must remember these properties. These are rather important. And then we will now try to see how shape functions can be generated in an automatic way, and how the process can be generalized.